Ritesh. Thank you very much for the introduction. So sorry for the delay. It's my first time to come to Iowa State University, but I'm quite familiar with the Midwest landscape and everything. I enjoyed discussing with the colleagues and seeing what you have here. This is really a pleasure. Given the diverse background of the audience and what we are doing in the electrical engineering department, so I thought my talk will be roughly an overview of this particular area that I have been involved with, say gallium nitride light emitting diodes or material research. The talk is roughly organized into two halves. The first half, this will be the tour guide and about what was the early history and what were the breakthroughs that enabled this fairly important area of solid-state lighting, primarily based on the advances in the gallium nitride material research. And then the second half, I will talk about more of my own recent research. It'll be more specialized, more focused. Be my recent activity in the past 5 years on the particular devices based on electrochemistry of gallium nitride. So here I'll try to give a few different scans of the historical development of gallium nitride or lighting. So we look at this field in different angles, different ways. This plot is the efficiency of different lighting technologies over the past 200 years. So the vertical axis, this is a semi-log plot. So we have the power conversion efficiency, power to power, of different lighting technology from Gen 1, you use gas burning, oil burning, kerosene burning, fire, and then this is from probably, the thousands of years ago all the way till roughly 1900. And for this type of a rather primitive way of getting the light out of a chemical, a combustion process, the efficiency is typically no more than like 0.5%. So this is a very primitive form of generating light until roughly the turn of last century, 20th century. Thomas Edison developed this filament-based incandescent light bulbs, so roughly here. And then from carbon to tungsten, and eventually the limited advance of the material of choice. And this is this kind of incandescent light bulb the performance is pretty much saturated at 3-4%, and lasted for 50-60 years until 1950. So the incandescent is based on black body radiation, as most of us know, until 1950. Then the gas discharge-based, the plasma-based lighting, I believe all these fluorescent tubes are based on the discharge of a mercury vapor, and that gives a UV light, and that the electron transition gives photons, and the photons are then converted by the phosphor coating and give a reasonably a nice white light. So this is beginning from 1950. And even with this type of advances, we're only getting somewhere around at most probably 20% of energy conversion. So still in all this lighting, 80% of light is 80% of energy is wasted. So 1950s, around the time also electronic materials start to become important. The semiconductors, silicon, germanium, and then 3/5 gallium arsenide. So we have light emitting red light emitting devices pioneered by not far from here, Professor Nick Holonyek's pioneer work at Illinois Urbana-Champaign. And red LEDs continue to, the performance and the efficiency continue to improve. So my research focus or has been in the blue and the green light emitting devices, and there is a very rapid, steep ascent in the device performance since the late, since let's say 80, 85 or so. And now blue light emitting devices have, in terms of IQE internal quantum efficiencies, close to 100%. And the white LEDs based on the blue LEDs are also making rapid progress. Now is comparable to fluorescent, probably slightly higher than the fluorescent technology. So this is roughly a quick history of the advance in the lighting technology. And in terms of the material research of this material, gallium nitride, I just use all these numbers it didn't show, but basically this is a linear scale for the past 40 years. It shows the development of at the beginning of this field, the gallium nitride. You do a Web of Knowledge or Google Scholar search with the keyword of gallium nitride, and you plot the number of papers per year and over the past 40 years. And he also showed, importantly, the different style of research, pursuing a new research direction. So the gallium nitride started around the same time that the gallium arsenide research began, late 60s, early 70s. And the gallium arsenide immediately took off with very good devices, LED laser diodes. And gallium nitride very quickly hit this plateau or just a barrier. And US started the nitride work, RCA labs at that time, and limited work at Stanford. Maybe there might be another place. Probably 3 groups work in gallium in the USA for no more than 10 years, but they could never make the breakthrough in material. Material quality is too poor, so eventually the US effort pretty much stopped before the end of the 80s. But a few Japanese groups, 2-3 groups picked up in the 70s. And they persisted for at least 10 years all by themselves with no other colleagues working on this seems a very next to impossible task of making electronically or optoelectronically viable gallium nitride until roughly from the middle to late 80s. There are a few breakthroughs which I want to get into some details. And once the breakthroughs were made, well, then there's exponential. Since this is again a semi-log, a log scale of number of publications. So this particular field went through in the early to late 90s, exponential growth. So a lot of things happened here in gallium nitride, and last year there's the Nobel Prize in the physics awarded to 3 pioneers. That's basically recognize their effort during this time. Professor Akasaki, Professor Amano, both of them, they from the same group. Amano was a graduate student when he made the breakthrough, and he spent a few years, spent his sabbatical in my lab. So that's in fact how some of the Japanese trade secret or technologies transferred to the U.S. So in that way, this is his advisor Akasaki and Shuji Nakamura. So this we call this AAN. And well, in fact, after the announcement of Nobel Prize last year in October, I was asked together with a few colleagues to write almost like a review or a commentary article about the breakthrough of their contribution. And then so I'm not going to get into details of this article, but in the course of preparing this manuscript, we decided to look at their contribution in a different way. So we try to gauge the intellectual impact of their papers. So we plot the number of citations from papers with the keyword gallium nitride or solid-state lighting. And for example, in 1970, there might be, who knows, 3, 4, 5 papers, each one cited 150 times or so. So you just put all this like a bit, almost like a big data era. So there's a scatter plot, and you see that after the 1990s, you start to see the density or the intensity of this field increases a lot. There's really a tremendous weight or mass in the publication. But the important thing here, I'm not sure whether you can see from afar, there are also the red dots. These red dots are from, sure, red is, our human eyes are not very sensitive to red color. So the red dots are from this Akasaki, Amano, and Nakamura's contribution. So their paper, you can see, tend to be on the upper left side, and that means they are ahead of the time in their contribution, and they received a lot of recognition. So these 3 points, 1, 2, 3, basically correspond to 3 particular breakthroughs. Each one is cited more than 1,000 times that turned this gallium nitride field around and make it possible for the light-emitting diodes. So these are the 3 technical breakthroughs. I want to get a little bit into details. All my trainings are in electrical engineering, but after my PhDs, I guess I downgraded a little bit into the material research, so I'm becoming increasingly more a material scientist. So some of these topics are related to material research, so I hope still you could follow some of my discussion. So here, why is it so difficult to grow gallium nitride? Why the U.S. Group couldn't make or survive the initial zeal in getting and to get high quality gallium nitride? The reason is because gallium nitride, this material at equilibrium, it has tremendously high vapor pressure. This is like a bomb, the pressure, 45,000 atmosphere pressure at high temperature. So it's very difficult to grow large size crystal, so you cannot produce wafers or substrate. Even to today, this is still a major obstacle. So people try to apply the technique from gallium arsenide or from, say, germanium of growing in a heteroepitaxial way, grow the thin film of gallium nitride on, say, different substrate. Sapphire was identified 40 years ago as probably the most promising substrate because number one, sapphire is aluminum oxide. It's thermally very stable. It can survive 1,000, 1,500 degree temperature. But there is a very large lattice mismatch. So when you try to grow gallium nitride on sapphire, the lattice mismatch is 16% difference in the lattice size. Typically, I'm not sure how many of you have done epitaxial growth, say gallium arsenide, indium gallium arsenide, those kind of a device construction. Normally, 1% lattice mismatch we would consider already difficult to manage, to handle. 16% is just really too difficult. So here, don't worry if you cannot read this. This is an excerpt from Professor Amano, his own recount of the breakthrough in 2002. This is years after he made the breakthrough in 85. Basically, he said that as a graduate student, his advisor asked him to try to grow gallium nitride on sapphire, and he tried 1,500 times. So, and every time it failed, and the surface of the crystal is like a frosted glass, so extremely rough. And okay, it looks like this. It's just an example. And he, in fact, said that the only reason he continued in La Jolla University to enter into the PhD program is because he had no hope of finding a job. So that was the only reason he continued. He said that they have 45 in his class. Only 2 people continue from master's course to PhD, and both because they didn't have a successful master thesis. So the problem is because when you try to grow gallium nitride on sapphire, because of lattice mismatch, gallium nitride does not want to land on such kind of a very dissimilar blue surface. You ended up with a very low density of the crystal colony, or we call nuclei. And in order to relax the tremendous, say, lattice mismatch, then these tiny islands, they tend to misorient with large angles of misalignment. Then as growth proceeds, these tiny randomly oriented islands eventually become rocks interpenetrating each other, and the surface is always bad and electronically or optoelectronically not very useful. So the breakthrough came after 1600 growth, and I guess luck strikes, and he was well prepared for this breakthrough. And he said that one day the machine, the apparatus, had a problem. There's a hardware problem. Turns out the RF heater, the RF generator used to raise the furnace to high temperature had some issue. He couldn't raise the temperature to normally the high temperature, and then he was forced to, this is a temperature and the time record of his experiment, he had to introduce a intermediate low temperature growth process. And so he tried this low temperature thing, and then during the growth, when the reactor recovered and he was able to raise the temperature back up, and then he finished the growth, and he was surprised. He said the surface looks extremely smooth and clear and transparent, like this. So. Thank you for asking. Yeah, feel free to interrupt me. So, yes, in fact, I asked Professor Akasaki, his advisor, about this question, and Professor Akasaki told me, he said that he feels gallium nitride, in his term, is a soft material compared to sapphire. Sapphire is in terms of hardness, it's like a ceramic-like, very hard material. He feels they need a handshaking layer with an intermediate property. So between a relatively soft gallium nitride and a extremely hard, just need with the electrical engineering term, a impedance match or transformer sort of a concept in material research. So they decided to try aluminum nitride. Yes, but more than that, they tried aluminum nitride already for a few years, and the result was not good because they prepared aluminum nitride at high temperature. And then so this, when the apparatus breakdown happened, they were growing aluminum nitride at a abnormally low temperature, and then that was the key. So after that, if I may continue, at the end of the experiment, he found that the surface become really, really transparent and very, very clear. And then he said that he just can never forget till, say, 20, 30 years later, the image he saw that day. He thought he didn't even complete the experiment. He thought there's no deposition. This clear glass is like the starting sapphire. He had to do additional measurement to confirm, oh, in fact, the gallium nitride has been deposited on this sapphire. So this was a major discovery. And in 1986, they published a paper basically saying growing, oh, by the way, all this, say, green, this slide with this kind of green format. This is, I asked Professor Amano to send me his Nobel lecture. So this is, of course, courtesy of him. So he said that gallium nitride on sapphire give you big crystals and very rough surface. But with insertion of a buffer layer, the surface become at least optically smooth. Okay, and then the second breakthrough is about doping. So up to this point, for any kind of semiconductor, you need to make it N-type and the P-type, especially for diode, for optoelectronic devices. You want the injection of minority carriers. So for gallium nitride, this is a gallium and the nitrogen. So the candidates for P-type dopant will be say on the 2B, 2A, these elements can replace gallium and then give you one missing electron or a hole as carriers. So the candidates at that time is zinc, cadmium, magnesium. Mercury is, well, vapor pressure is too high and not easy to handle. Beryllium is too toxic. So people were trying zinc, cadmium, and the magnesium. Nobody really could get a very convincing, reproducible P-type conductivity. Even though a few years ago, this is a Stanford group, they at that time reported putting magnesium into gallium nitride could give you some blue luminescence, but this result was never reproduced, and this seems to be a very mysterious result, and they didn't really know why, what limits the P-type conductivity of gallium nitride. So again, Amano, this group made the first two discovery or breakthrough. What he discovered purely accidentally is after the growth of gallium nitride with magnesium doping, he looked at the sample in an SEM chamber, scanning electron microscope. So as he moved the electron beam across a magnesium-doped gallium nitride, he started to notice the area where the electron beam rested across, there is a characteristic blue luminescence. And while the region that is not irradiated with electron beam does not give a luminescence. And he started to hypothesize that some energetic beams convert the magnesium doping into a more active P-type gallium nitride. And turns out electron beam removed the hydrogen. And then, years later, people study and had now good understanding that the hydrogen passivated the magnesium acceptor. This is well known in the silicon industry, and for probably decades, the hydrogen passivation in silicon. And Shuji Nakamura later found out one can just use a high temperature annealing to drive out hydrogen to produce the p-type conductivity. Well, this is okay. So we are now roughly to around 1992, after the first two discovery or breakthroughs. Now gallium nitride had reasonable quality, and there's a p-type conductivity. At that time, if you are tracing after blue-green light-emitting devices in 91, 92, at that time I was a graduate student. There are two contenders, so there's a race. The majority of people, including my advisor and myself, we work on this zinc selenide. This is a 2,6 semiconductor. Lattice matched to gallium arsenide. You can grow fairly high quality zinc selenide. Band gap is in the blue, so you can make a blue or blue-green light emitters. And there's also gallium nitride, and at that time, the first two breakthroughs have been made. But the sentiment at that time was, okay, this is a slide from Nakamura. Basically, we just jump to the punchline. Most of people say gallium nitride has no future. Gallium nitride people have to move to zinc selenide material, and nobody believed gallium nitride, even in 92, after the first two breakthrough. Why is that? Mainly because even at that time, this dislocation density is still 10 to the 9th. Dislocations are a line, like a linear crystalline defect in semiconductors. So this is essentially, after one uses a buffer layer, you can have a gallium nitride crystal with this dark lines, dislocations, typically 10 to the 9th. That's what 1 billion of dislocation per square centimeter within this area. And at that time, based on all the, how should I say, the history, the conventional wisdom from gallium arsenide, even from gallium nitride, I'm not sure if you can read the font. From the 3.5 history, dislocation is a killer to the efficiency of light-emitting devices. We plot the normalized efficiency versus dislocation density. There's this very steep drop. 10 to the 4th, 10 to the 5 dislocations, then LED, the efficiency will drop, including gallium nitride. And the gallium nitride at that time on sapphire, the dislocation density 10 to the 9th, so nobody thinks it's ever possible to make any kind of gallium nitride LED that will give any light. I'm sorry?
Can you anneal to get rid of the dislocations, or do you lose the nitrogen?
Yeah, okay, thank you for asking. This is really a good question. Dislocations in gallium nitride, they are not that mobile. You need to heat it up to 1,1300 degrees, and then by the time you reach that temperature for dislocation to start to become mobile surface, as you correctly pointed out, you will lose the nitrogen. You need to find a way to cap or protect the surface. Yeah, so that was the main issue. But presumably, if you anneal gallium nitride at a very high temperature, dislocation may glide and somehow interact and annihilate. But at that time, it was not possible. So this is pretty much the state-of-the-art material. The question is, how do you get a high efficiency? And this is Shuji Nakamura's contribution. He figured out, he alloyed gallium nitride with indium. He added this indium into gallium nitride and narrowed the band gap. And there's this very astounding paper in '94. Basically, he showed using indium gallium nitride as the LED. The light is very, very bright. I still remember in '94, '95, he went to a lot of conferences, really mesmerized a lot of people just with this showing a very, very bright blue LED in his hand. And the key is to learn to figure out how to grow indium gallium nitride. And what is amazing is adding indium into gallium nitride, then the line become like this. So indium gallium nitride, even with the 10 to the 9th, 10 to the 10th dislocations, you can still have a near unity, very, very high efficiency LED. Of course, if you increase the current density, efficiency will drop, but it's quite still very, very respectful. So I'm just telling you, probably 10 years later, what's the people's finding about the cause of this insensitivity, defect in sensitivity for indium gallium nitride. And the story is as you add indium into gallium nitride, indium and the gallium, these two atoms, the sizes are very different. So they don't like to be mixed together. Right? They like to segregate. Almost like some segregation in our culture that tend to stabilize things sometimes. So if you prepare indium gallium nitride micro or nanoscopically, you have different clusters of indium-rich, indium-poor regions. So if you look at the electrostatic potential or band profile on the spatial scale, it's like you are in a very mountainous terrain, and with a peak and the valley. And these valleys, potential valleys, tend to trap and localize injected electrons and holes. So the diffusion length of electrons and holes are greatly reduced, and they are preserved from getting consumed by the high density of dislocations. And this is the leading, and I believe this is by now a pretty accepted theorem of why gallium nitride LEDs, even in the presence of a very high density of dislocation, can still be very, very efficient. So this is basically what happened with these three breakthroughs. Then the field changes course. Instead of staying dormant, it went up like that way. So lighting accounts for, in terms of our usage of electrical energy, lighting accounts for 30%, plus minus 3 or 4%. So any kind of advance in the lighting efficiency of the lighting fixture will immediately impact our the energy consumption. And currently we are, I would say, I'm pretty sure most of you probably do not have LED light bulbs at your home yet, right? Or some of you do, yeah. Probably for faculties, yeah, not for graduate students yet. So the reason is I have a few in my home also, but they tend to be still quite expensive. So the issue is now it is basically the reason we are not seeing massive or complete displacement of the traditional tube-based lighting fixture is because of this issue, the cost measured as $1 per lumen. So what is, given the per unit lumen, what is the amount of dollar people willing to spend, whether $20 or $30 per light bulb? That seems too expensive. And the projection is manufacturing efficiency. We need to continue resort to the scaling up to drive the production costs. But at the same time, LED performance still needs to go from, say, 20% or so right now, the power conversion efficiency. We would like to go to 40%, even to 60%. How do we get there? And the issue Okay, so this is facing all the people in my community, is this we call Droop issue. And Droop, that's a decrease of LED efficiency. This is a measurement of the internal quantum efficiency of LED, and as a function of a current density. And these are commercial LED devices, pretty much state of the art. In the blue wavelength, it peaked at 80% IQE. This is an excellent device, but you notice if the current density is only 1 amp per square centimeter. If you go to 100 amp per square centimeter, it already dropped to 60%. So we call this is a current droop problem. In order to make the light bulb inexpensive, really the way to do it is for a single chip. You want to drive it as hard as possible and maintaining the same efficiency. So you fabricate, say, one chip. Instead of operating at 1 watt, you need 10 chips. If one chip you can operate at 10 watts and getting 10 times the photon, that will drive the cost down. So this current droop is an obstacle for getting to a higher power LED. And the other is a wavelength droop. Wavelength droop, as you go to higher and longer wavelengths from blue to green, efficiency also dropped. So these are all material research issues. This is a loaded, okay, so maybe there are various reasons and models related to why there's a droop problem. There's an internal loss, carrier transport. These are rather active research topics. For now, I think I probably will. If you really want to know the details, we can talk about that maybe later. So, well, this is not a summary yet. This is the end of the first half. The observation is LED technology is becoming commoditized and outsourcing to Asia. And for most of the colleagues in academia, we really need to find out what are the key new emerging topics, because right now the technology in companies is really ahead compared to a lot of the university groups. Most of the LED companies, they can produce brighter and brighter LEDs, but they don't have, we are the victim of our own success. But other than silicon, gallium nitride remains probably one of the most important semiconductors. So what are the other possible new directions? Okay, so I will talk about a few things we did in the past 5 years. The first one is about applying electrochemistry to gallium nitride. This is a very material research topic. What we found is when we apply with a wafer of gallium nitride, if you put a gallium nitride into an electrolyte and apply a bias, this process is called, say, anodization, or you can say electrochemical etching. Interesting enough, gallium nitride will start to turn into a porous structure. You start to create like bubbles, or gallium nitride turn into a sponge or a foam or a cheese like a material with a lot of tiny holes. And this is a phase diagram here. It turns out as you increase the applied bias, this electrochemical etching bias, or if you increase the doping, you can gradually increase the degree of porosity. Eventually, you can etch away gallium nitride. And this process is electrochemically selective. So why do I mention this? So you can do a lot of things with this new form of gallium nitride. And I'll just give a few examples. The first example, when you put holes into gallium nitride, the index of gallium nitride changed very dramatically. You put air into gallium nitride, and then this is useful for photonic device design. One particular device we're trying to make is a vertical cavity surface emitting device. So as we know, gallium nitride LED is now commercially available. There's a gallium nitride power devices, gallium nitride edge emitting laser, but it has been rather difficult to make VCSEL, vertical cavity surface emitting laser. So here, these are the two simple drawing of a laser, edge emitting laser. By the way, edge emitting laser now is used in some of the higher end BMW and all the high beam. They are using the gallium nitride laser diode as a high beam for like a white light to improve the directionality and to minimize the diffusive light that blind the incoming driver. That's like a safety feature. But vertical cavity, we want to form a microcavity by using what we call the distributed Bragg reflector. These are quarter wavelength layers with alternating index of refraction. This is one of the holy grails in gallium nitride devices, but it's not very easy to make because it's not easy to get the index contrast, optical index contrast in this microcavity design. So in the aluminum gallium arsenide, this field, people have built beautiful, now it's commercially, in fact, it's becoming the mainstream infrared and the red laser diodes. These are all made by pretty much using the VCSEL, vertical cavity lasers. And because aluminum arsenide and the gallium arsenide, this plot is a band gap and the lattice constant. Number one, they have a sufficiently large index contrast. Optical index is different, so they can create the constructive interference. But at the same time, they are lattice matched. But for gallium nitride and aluminum gallium nitride, the index contrast is not that large, but the lattice mismatch is huge. So when people try to grow aluminum gallium nitride, this kind of alternating layer to form a distributed Bragg reflector, you run into cracking and all kinds of problems. So what we did, this is using the electrochemistry. We created, because we can grow gallium nitride layer with a different doping. We can have a lightly doped layer, heavily doped layer, and lightly doped layer. And if you, for example, if I apply an etching bias of 3 volts, then the lightly doped area will be no etching, nothing will happen. But the heavily doped area will become, this region we call nanoporous region, they can form pores. And this region is still crystalline and electrically conductive, but the index of refraction changed dramatically. So this is a way to create a waveguide or to create reflectors. So what we did, we grow gallium nitride and alternating the doping, and we process this and we process opening trenches and do the lateral oxidation, lateral porosification, to form these tiny pores. So this is well, maybe you can't really see clearly. We form a nanoscale porous and solid gallium nitride alternating layers, and in this way we can make a fairly high quality. This is a reflector here. This is a reflectance versus wavelength. So this is essentially like a green mirror. The reflectance peaked at nearly 100%, and you reflect the green light. And such kind of epitaxial structure is very useful for constructing, microcavities. And it just shows that it's very easy to make, say, red mirror, green mirror, and the blue mirrors. And with this, we also tried to form gallium nitride microcavity, and we could optically pump it into lysine. This is a blue VCSEL, and currently we're in the process of making an injection, electrical injection VCSEL, inject current through a nanoporous medium, and this is one of the projects. Okay, so maybe another 5 minutes. I'll quickly tell you the last thing, that we also try to make gallium nitride flexible, and making gallium nitride into a very thin nanomembrane on the order of 0.1 to 0.3 micron, or 50 nanometers to maybe 500 nanometers. And we can make LEDs and make FETs. So this, we think it's a unique way to make inorganic semiconductor flexible. The majority of the flexible devices tend to be made by organic materials, organic OLEDs, organic transistors. But in terms of the performance, inorganic materials intrinsically have a better transport and optoelectronic behavior. So the goal is to make very, very thin semiconductor membrane. And this is a particular challenge for gallium nitride, because gallium nitride is chemically very, very inert. So we use electrochemical etching. The procedure is we have a sacrificial layer. This is an epitaxial structure. Grow something. There's a membrane layer, and then we have a N+ heavily doped gallium nitride, and this layer can be electrochemically selectively etched away. You just drill a few holes. These are openings, and then apply anodization bias. Then eventually this top layer will float, and this is a method we just show you. We grow undoped gallium nitride, and this is about 90 nanometer of gallium nitride. This is a sacrificial layer, and lateral electrochemical etching is a unique way to selectively attack gallium nitride. While these are a few examples, we can make a fairly large area, a centimeter square or bigger, a few centimeters square, a thin, flexible nanomembrane. Structurally, they are single crystalline, as good as the as-grown gallium nitride. We made LED, and this LED is a 300 nanometer. The total thickness is 300 nanometer, including N-side, P-side, and the indium gallium nitride quantum well. Everything is in a membrane. We transfer the membrane to a aluminum-coated silicon and put a contact. So this become a very, very thin film nanomembrane LED. We think this could be used for interface with biological probing, and we are now discussing with some brain science group, thinking about whether there are ways to do the brain topology or mapping using this individually controlled thin LED array in a non-invasive way for optical excitation. And we also made HEMT. So this HEMT is aluminum gallium nitride. Sorry, it didn't show up this kind of membrane. This membrane, okay, I'm going to skip the structural characterization. X-ray diffraction basically showed it's quite beautiful and high quality. We transferred a very thin membrane to silicon dioxide, and it shows a typical transistor characteristic. And okay, the gate leakage is fairly low. This is a 25 micron by 2 micron. the gate is here. I'm not sure whether you can see. This is a very narrow gate here. And the transconductance reaches roughly 2 millisiemens. So we also transferred HEMT to a PET, a flexible a surface. In that case, the LED performance is unaffected, and at the same time, the on-off ratio is maintained at least maybe 5 or 6 order of magnitude. This could be useful for sensing and for wireless power transistor or Wi-Fi purpose. Okay, so I'm already over time. So just in conclusion, I would say from my point of view, this development of a gallium nitride material is really a very inspiring a story for young researchers and for many of us, that we should continue to persevere in what we consider, what we believe, what we think is promising. And in a more application specific context, solid-state lighting is going to come in once we solve all the remaining problems, mostly related to the cost reduction, to the further improvement in performance. Second revolution in semiconductor, in replacing tube-based lighting fixture by solid-state lighting. That's going to come. And I believe in terms of gallium nitride, we still have a laser, power electronics, energy, and life science area. These are remaining frontiers for gallium nitride to continue to find its usage. Okay, so thank you for your attention.